So let's look at the second law of thermodynamics. The total entropy of a system and its surroundings always increases for a spontaneous process and remains unchanged in an equilibrium process. So we're going to calculate the change in entropy. That will be the S final minus the S initial. The appendix 2 is in your Chang overview and it contains the thermodynamic data. So let's look at a simple question. We've got water solid going to water liquid. So you look in your appendix 2, you assign the entropy of the water. That's a solid. The entropy of the water, that's a liquid. And then here's your final, 69.9. Here's your initial, 41. So the change in entropy is always going to be final minus initial. And so for this process, it's 28.9 joules per Kelvin. So now we have the third law of thermodynamics. Again, you're going to want to memorize the second law, memorize the third law, because you never know when they come up in a standardized testing situation. So the third law is that a perfect crystal at 0 degrees Kelvin has an entropy of 0. So now we're going to look at standard entropy. We use this little superscript 0. This is the entropy value for standard states of the species. So the standard state is a pure substance, 1 atmosphere, 1 molar, and you're going to need to know this. So entropy usually increases when a reaction in which a molecule is broken up into 2 or more smaller molecules, a reaction in which there is an increase in the moles of gas, going from a solid to a liquid, going from a solid to a gas, going from a liquid to a gas. So now we're going to predict the sign of the change in entropy at standard state for each of the following reactions. So this is a qualitative look at entropy. So we're going to start with the fermentation of glucose to ethanol and carbon dioxide. So here's the equation for that. This is the formula for glucose, formula for ethanol, formula for this carbon dioxide, and then we balance the equation. So after you write down your balanced equation, then you're going to label them. Solid, liquid, gas. The gas is much more disordered than a solid or liquid. Our entropy increases, so our change in entropy at the standard state is positive. So let's look at another one. The preparation of urea, this is a formula for urea, from ammonia and carbon dioxide. So first we write our balanced equation. 2 ammonia gas plus carbon dioxide gas goes to urea, solution, and water, which is liquid. So then we label gas, gas, solution, liquid. The entropy of the gas is much more than the entropy of the solution or the entropy of the liquid. We're losing entropy, so the entropy decreases. So our change in entropy at the standard state is negative. Next, production of carbon dioxide gas and hydrogen gas from carbon monoxide gas and steam. So here's our equation. We label everything gas, 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 gas. We cannot predict. We have gas from both sides. Okay, next, we've got the decomposition of calcium carbonate solid to calcium oxide solid and carbon dioxide gas. So we write the equation. We label solid gas. The gas has a greater entropy than the solid. Our entropy increases. Our delta S at the standard state is positive. Okay, so next, the formation of carbon disulfide gas from carbon disulfide liquid. So we've got liquid going to gas. The liquid to gas, the entropy of the gas is much greater than the entropy of the liquid. So the entropy increases. Our delta S of the standard state is positive. So next we have production of mercury 2 oxide solid from mercury liquid and oxygen gas. So here's the liquid mercury, here's the oxygen gas. It's going to form solid. We've got liquid and gas going to solid. Liquid and gas has much more entropy than solid. So we're losing entropy. So we have the delta S at our standard state is negative. Our entropy decreases. Reaction of sodium peroxide solid with water to produce sodium hydroxide aqueous and oxygen gas. We've got solid, liquid, solution, gas. The entropy of a solution in a gas is greater than a solid or a liquid. The delta S is positive because the entropy increases. Okay, so now we're going to look at another example. So the question is giving you the balanced equation and asking, does the entropy increase or decrease when the following reaction occurs? Got 4 ammonia gas plus 5 oxygen gas goes to 4 NO gas plus 6 water gas. So our answer is that both the reactants and the products are in the same phase. So when you have this situation, you're going to add up the number of molecules on each side. So on this side, we've got 4 plus 5 is 9 reactants. Goes to 4 plus 6, which is 10 products. We have 9 reactants going to 10 products. The number of molecules of the gaseous products is greater than the number of molecules of the gaseous reactants. Entropy increases. Therefore, our delta S at the standard state is positive. Okay, so now we're going to do quantitative. So we're going to calculate the delta S. So the delta S is the summation of the stoichiometry of the products minus the summation of the stoichiometry of the reactants. So let's look at an example. We're going to calculate delta S at 25 degrees for the formation of urea, and we're given the delta S for urea. So these values are in the back of your book. So we put them in, 193 for ammonia, 213.6 for carbon dioxide, 174 for the urea, 69.9 for the water. So these are the entropy values in the table. And the units are joules over mole Kelvin. So we're going to have to use our coefficients. So 1 mole times 69.9 joules per mole Kelvin, that came from here. 1 mole, 174 joules over mole Kelvin, that came from here. These are our products. We're going to subtract our reactants and include the stoichiometry. So we've got 2 here, that's our 2 here. 2 moles times 193 joules over mole Kelvin. 1 mole here, so 1 here. 1 mole times 2, 13.6 joules per mole Kelvin. The moles cancel. So you end up getting this as your answer, minus 355.7 joules over Kelvin. And now we're going to look at free energy. This is called Gibbs free energy because of the Gibbs dude. You don't need to know the dates. This combines the first and second laws of thermodynamics, so it's really quite smart. So delta G equals delta H minus T delta S. You're just going to want to memorize this because you're going to see it in biochem. This is at constant temperature and pressure where the H is enthalpy. So you're going to want, just a second. Really? Yeah, I think I stopped it. I hope. I don't know.
That's my face mask before I even got in the store.
Oh.
So I was just breathing into my eye.
Okay, well, hopefully you're okay. Okay, so you're going to want to know this. When the change in free energy is negative, the reaction is spontaneous, it gives off energy. So for sure, know this. When the change in free energy is 0, the reaction is at equilibrium. When the change in free energy is positive, the reaction is not spontaneous and it requires energy. So absolutely know these 3 situations. Just memorize them. So let's look at the standard state. This is again when we have our standard state situation. So it's delta G at the standard state equals delta H at the standard state minus T delta S at the standard state. So memorize this. So now we have a question. We're asked to find the delta G for the reaction of a nitrogen gas plus hydrogen gas produces ammonia gas at 25 degrees C. So in this case, you're going to have to go the long way, and you first have to calculate the enthalpy, put it in here, the entropy, put it in here, and then the temperature to change to Kelvin. Let's just do this step by step. So we're going to start with the enthalpy. So here's our reaction. These values are from the book. So 0, 0, minus 46.3. The units are kilojoules per mole. So we've got 2. We use that here. And we put our minus 46.3 here. Be very careful with your positives and negatives. And then it was products minus reactants. So here we have 1 mole, but it's 0. 1 mole, but it's 0. So when we do the math, we get our enthalpy is minus 92.6 kilojoules. The moles had canceled out. So now we're going to do the entropy. So these values are again from a table. So we plug in our value for our nitrogen gas, hydrogen gas, and ammonia. The units are joules over mole Kelvin. Be careful your units. This is in joules. So we use our coefficients here. We use our coefficients here. We've got 3 moles. So again, we've got 2 moles, 193 joules over mole Kelvin. That's our products. Minus our reactants, 1 mole, 191.5 joules over mole Kelvin, plus 3 moles of 131.0 joules over mole Kelvin. Again, this is products minus reactants. So the answer we get is a minus 198.5 joules over Kelvin. We're going to convert that to kilojoules. So our change in entropy at the standard state is minus 0.1985 kilojoules over Kelvin. Now we're going to plug this into our equation. So our delta G is minus 92.6 kilojoules. We got that from here. Minus 298, that was our temperature. Remember, this was a minus. We plugged it inside our parentheses. We make sure that this is in kilojoules per Kelvin. And so our final answer is minus 33.4 kilojoules. That's energy given off because the delta G is negative. Okay, so let's look at the standard free energy of formation. This is the delta G of formation, standard state. It's when 1 mole of substance is formed from its elements in their most stable states at 1 atmosphere and 25 degrees C. It's called the standard free energy of formation. So to get the delta G for a reaction, you would take the sum of the stoichiometry of the delta G of formation of the products minus the sum of the stoichiometry of the delta G of the reactants. So again, this is products minus reactants. Okay, so what is the delta G of formation for the production of ammonia gas from nitrogen gas and hydrogen gas? We're going to calculate for 1 mole of ammonia. So we would have 1/2 nitrogen gas plus 3/2 hydrogen gas to get 1 mole of ammonia. We can get our delta G of formation from our table in the back of the book. This is 0, 0. This is a minus 16.6. So I'm just going to simplify this because it's products minus reactants, and these guys are 0. So my delta G of formation at standard state for the formation of ammonia gas is a minus 16.6 kilojoules per mole. Okay, so let's look at another question. This is asking us to calculate the delta G at the standard state for the combustion of 1 mole of ethanol, and this is the formula for ethanol at 25 degrees C. So we write our equation. You guys are supposed to know that combustion means plus oxygen. We have to balance it. So we have ethanol, C2H5OH, plus 3O2, going to 2CO2 gas, plus water. You should know combustion of a hydrocarbon, or in this case, a hydrocarbon with an oxygen, is going to always give you carbon dioxide gas and water. So we plug in our values from our table. So this is the delta G of formation for our ethanol, 0 for the oxygen, minus 394.4 for our carbon dioxide, and minus 228.6 for our water. The units are kilojoules per mole. We're going to use the stoichiometry. So here's our 2. We plug this in here. Plus here's our 3. We plug this in here. So these are our products. Minus, we have 1 of these, and I just ignored that. And then I got this from here. Please know I didn't make a mistake. Oh, that's fine. Well, yeah, the speaker allows a lot of times when people are recording it.
That's so that trail open. Go down the hill and move it. So I went down the hill almost all the way to this area. And I had to skate back up the hill. So I could make a turn. And then I was skating there.
Yeah.
I realized there's like ducks and geese. I had to go up the stairs.
Yeah.
Go back down the stairs. I didn't bring gloves, so I had to pull my wire all the way down.
Jeez.
Just the handrail. There's a few people there walking on stuff. So I went as far as I think it's right at Boulevard. Lost it. No, can't go into the street. I went a decent distance. That's what they should do. Little creek that runs right along the trail.
Yeah.
It used to be a railroad. All right.
Well, the answer is right.
Everyone had face masks because I was one of the
Nice.
few not wearing a face mask. People would pause and veer over to the
Oh,
side and let me go by. I had the face mask on, but like I said, it was like, okay, it was on my face, right? Going to one strap, and the air was shooting up, so it's fogging up my right eye.
well,
So I thought, okay, if I'm gonna fucking get it, I'm gonna get it no matter what. It's fucking going
yeah,
to
we're
shit.
probably going to have to buy some face masks.
I was talking maybe a handful of people did not have. Wasn't
Yeah,
surprised.
well, when I went to the post office, everyone had face masks pretty much.
And they have glass partitions, plastic, whatever the fuck it is. See their partitions, you and the cashier.
Yeah,
Like
I saw
Target
that when
too.
they, yeah, when I went to Target, they had that.
Thing is, what's the point of having that if I have to bag my own fucking groceries and she has to put the groceries right next to her own fucking stand? So we're breathing.
It's just
This is how
for
far we're
looks.
breathing from each other.
Yeah, it's just for looks. It doesn't do anything. If
So-
someone sneezes, the glass will get some of it, but there's such a big
There's
hole,
holes right
such a
there
big
and
hole
it's all
there.
around. So we were breathing
No,
some
it's
air.
yeah, no,
Oh.
it's not gonna do
There's a few
anything.
seconds where I tried to hold my breath.
No,
I
you have to
thought, no.
wash your hands.
So only thing I touched on bare hands was the screen because my fucking glove just smudged the screen. Good point. Well, I used the.
Oh, good, okay, yay.
So I wash my hands and I use my gloves to push the cart. I use my gloves to get the fucking groceries. I use my gloves again to put away the fucking cart. I use my bare hands to put away the groceries. I don't fucking get the whole fucking point of this shit. So my groceries, I don't fucking know. I'm just gonna fucking eat them.
Stephanie says to wait 4 days. The virus can last on surfaces 4 days, but it also depends on the surface.
So my gloves are touching the same fucking thing. Like, what's the fucking point?
And then you're supposed to take your gloves off very carefully like that.
I just fucking. It was nice getting, like, I could go wherever I want and no one get in my way. I was like, fucking, I played with them. You should see some guy. There's some guy that turned inside out. He just stood there and froze. I was like, doop a doop doo.
Well, in Orange County, it's not mandatory to wear a mask.
No, it's fucking broken, and there's 4 holes right here because my big ass fucking nose and the strap was broken. I'm just creating fucking vortexes in my face. I just tried to get crackers. Got cookies, but then there's a guy shit there, so I forgot to go around.
Oh yeah, I'm low on crackers. I ate all my crackers.
Oh, I have like half a little bag.
I have no crackers. I love those Ritz crackers. I have none.
Can you get
So I
bread?
figured out I can stop the video. I made a little mistake there, but the answer's right.
Yeah. I was gonna get bread, but then by the time I ate the bread, it'd be halfway through it.
Yeah, that's
Wait a
fine.
week and get bread. Target, that's how I go in that Target. It's never really crowded.
Oh, the Target in Brea?
Yeah.
Yeah, I like it.
So every time I go to the fucking grocery store, it's packed.
Yeah, I don't even want to go to Stater Brothers right now. Oh, I ordered peanuts online. I remember I had done it before, but I had ordered too many peanuts before. But so this time I ordered some peanuts online because I don't want to go to Stater Brothers and get peanuts.
Fucking use my gloves. No fucking point in wearing. I'm still touching all this shit. No fucking point that goddamn partition. I felt like
People are stupid. They don't realize that the partition is not going to do much of anything.
I felt every breath. I thought, oh my god, which breath is it? The fucking virus.
Yeah, the face masks don't stop the virus. You have to have a particular size of this part, the holes, and that's the N95. It's just the face mask would stop you sneezing. Like if you sneeze, you would sneeze inside your mask. So the whole idea about masks, no, it just stops the sneezing. So it would still help because it would stop the people from sneezing.
Yeah.
Okay, I'm glad the answer was right. I just forgot one little minus there.
Should have. Forgot to bring my phone. Yeah, it's great picture.
That's good.
But I don't know if I want to go. Yeah, but coming back from Whittier, we would take that one crazy guy. We would take Berry Street, this little street, and we would
Oh, yeah.
and that you swirl up the parking structure that ends on Birch. I went past that little street we biked down years ago.
Oh.
I never really noticed that trail there because we biked and it's sprint up this is before all the businesses would open, there'd be no one there, so it's sprint up the parking.
Yeah.
I got coronavirus the guys today.
Well, wash your hands.
No one sneezed or coughed on me. I already washed.
Okay, you should be okay then.
Fresh groceries, all that stay there, man.
Okay, so there is a negative here that I forgot to put, but I checked and the answer is correct. So if you could please make that correction of putting the negative here. So if you look, oh, that doesn't work, does it? So if you look here, there was a negative, and so it does, oh, you can see. Okay, so this is a negative 174.8, so it still stays as a negative here, but the answer is correct. Let me erase that little guy because it stays on my screen. Okay, so this makes sense. The combustion of ethanol gives off a lot of energy. So let's look at an interpretation of free energy. The delta F, delta G is the maximum energy available to do useful work. It is possible to obtain maximum work from some reactions, for example, batteries. So let's look at the idea of coupling reactions. So you're going to use the energy given off from one reaction to drive the other reaction. You're going to see this a lot in biochem. So we have this reaction with the delta G of positive 1487 kilojoules, and we have this reaction with a negative 1543, and that's kilojoules. So if we add them up, we're just adding these up. So here's our iron oxide. Here's our carbon dioxide. Our oxygen gas cancels from both sides. And then, I guess that's 4. And then we're okay here with the 6. So if you would just take this 4 and put it there. So we add up the reactions on both sides, and then we simply add up the delta G's. So we take this delta G from the first reaction, we add this delta G from the second reaction, and we get a negative 56 kilojoules. Remember, negative is good in this situation. That means energy is available to do work. So the energy from this reaction made this reaction go. So that's the idea. Okay, so let me erase this little guy. Okay, so we're going to do the free energy and equilibrium constants next time.